Hello and welcome everyone. Today I want to talk about something only Japanese or exotically named super grandmasters are allowed to touch. Doubling. And so, to minimize the damage to my reputation and to backgammon in general, I'm going to steer away from opinions, judgments and bots, and try to stick to the absolute truth, down to 7 significant digits when possible. Inconceivable, you say? Yes, it's unattainable in general, but possible if we limit ourselves to a small corner of backgammon. A very small corner. Pure bear-off.
Off to the races.
0.5 billionths of the total game space, in fact. And yet, we face them occasionally. Black, a former world champion, faces 2 times world champion red. Black rolled double sixes.
Oh, double sixes.
And red responded with double fives. What is the right cube action? For that, we need 3 values. Black's cube full match equity after a no double, Black's cube full match equity after a double take, and Black's cube full match equity after a double drop. I take it all of you are familiar with match equity. It's just the match winning chance in disguise. +1 is a win, and -1 is a loss. So 0 is 50%. Easy. The double drop, which we get from the equity table, is 0.295 blah blah blah. The no double equity is 0.216 and so on. And the double take is 0.206, etc. etc. Since no double is greater than double take, the correct action is no double take.
5-4 is a perfect number. Mochi really needs to have a 6 here. 4-3.
Here the cube for no double is 0.255 and double take is 0.285. So black should double. And since 0.285 is smaller than 0.295, red should take.
Alright, I'm giving him the thing. This was good enough for me. He didn't roll a 6, you give him the thing. Just for the sake of distribution, right? Anytime Mochi rolls a 5, that gap is gonna kill him, right?
Yeah.
Whereas anytime Frank rolls any number, everything just plays forward or takes off to a good spot, right?
Yeah.
All of his big numbers play perfectly. All of his little numbers will also creep forward without wastage. But anytime Mochi rolls a 5, it's death.
Yeah.
So this has to be a cube, but the question really is, it a take? And
I saw Mochi. Look at
the
Mochi.
cube is easy though. The cube is easy. No, cube please.
Oh, Mochi was ready.
Oh, you gotta cube that. Mochi is so lucky he didn't cube that.
Actually, if I was looking at the Mochi's face, I would push the cube. You know.
It's getting worse. Double take reached 0.321, way over double drop. So it's a double drop.
Oh, he didn't cube that one either?
Yes.
Oh no, there goes the neighborhood for the PR.
Black ignored Justin's desperate pleas and rolled on once more. He finally relented here.
The bear off got the PR on this one, huh?
I find it fascinating. Bear off is the simplest part in backgammon. Some call it trivial. And yet, even former world champions aren't immune to momentary lapses of judgment. That said, these are rare, and it's amazing how quickly and accurately Justin figured out the correct action at each junction. Mochi too by his face. But most of all, I'm struck by the gulf between human reasoning and the cold hard truth, represented by those boring numbers. Well-reasoned arguments versus numbers out of nowhere. Can they be that accurate, you wonder? Don't worry, because I'm going to provide a detailed explanation. Or maybe do worry, because I'm going to build doubling from scratch. As if you were a seasoned Balkan/Middle Eastern player who never saw a doubling cube in her life. And I will start with the most trivial position, but please bear with me. In traditional sheshbesh, black either wins on the next roll or loses upon the dreaded 1-2. Oy vey. Since there are 2 such rolls, black wins 1 lira 34 out of 36 times and loses 1 lira 2 out of 36. Her cubeless equity, the expected amount of money she wins, is 89 kush. In modern backgammon, black can offer to double the stakes by handing white the doubling cube. White can either accept the double or reject, instantly losing $1. How does black figure out what to do? If she doesn't double, the game proceeds as for cubeless, so her no double cubeful equity is 89 cents. If she doubles and white takes, it's again the same as cubeless, but doubled, so a cubeful equity is $1.77. And it's $1 if white drops. Both double take and double drop are more than no double, so white should double. And black, by the same numbers, should drop when doubled, since $1 is less than 1.77. And so, the correct cubeful action is double drop, and the cubeful equity of the position is +1, since with correct play, black wins $1. Here, black wins unless she rolls 1-2, 1-3, 1-4, 1-5, and 1-6. 5 non-double rolls. So a total of 10 numbers out of 36, giving black an equity of 44 cents when not doubling. Twice that much, 89 cents when she doubles and white takes, and $1 when white drops. 89 cents and $1 are more than 44 cents, so black should double. White will lose 89 cents if he takes, and $1 if it drops, so should take. With perfect play, it is a double take, and the position cubeful equity is 89 cents. And here, black has 17 immediate winners and 90 losers, so her cubeful no double equity is -6 cents, and double take is -11 cents. No double is greater than double take, so it's a no double. Now, why did I bore you with this kindergarten stuff? Because it is, believe it or not, all the doubling theory we need. Black doubles when no double is less than both double take and double drop, and white takes if double take is less than double drop. The rest is details and engineering. Quite a lot of it actually, but it always comes down to those 3 numbers. Here black has, as before, 10 immediate winners, but after a double take and black rolling 5-1, we reach our first position, only reversed, so white can redouble black out, which means it is identical to position 2 in terms of equities. This position illustrates redoubling. After black doubles to 2, white owns the cube, which means only he can redouble to 4. That's why he tucks it safely on his side of the board. Black will be able to double to 8 after taking a 4 cube from white, and so on. Now what about this position? 6 and 5 with something greater than 1 wins on the spot, 16 number in all, and also double 2, double 3, and double 4, giving a total of 90 numbers. But it's not a last roll position, and play goes on after the other 17 rolls. Say black rolls 6-1. We get to position 2, only reversed, and we already computed that white's equity is 88 cents, which means that black's equity after the 6-1 is -88 cents. This is true for any shake where black needs only 1 roll to finish bear off, which is any roll except our favorite, 2-1. When black rolls 2-1, she has 3 moves: 2 off and 5-4, 5-2, and 5-3, 2-1. You instinctively know which move not to make, but we want absolute truth, not intuition. We need to systematically compute the cubeful equity of each possible move and pick the one with the lowest equity for white, which gives the best move for black. In this case, it turns out 2-1 and 6-1 come out the same. After a double by white and a take by black, and white rolling 1 something, black can redouble white out. Here the same sequences hold after an initial double, so double take is twice no double. But generally we have to repeat the process for double take. moves and cube actions might depend on the cube situation, mainly because not every double is a redouble. Now you begin to see what I meant by details and engineering. Computing any equity requires chasing every rabbit hole all the way down. Computing it over the board is out of the question. Almost any roll permits multiple legal moves, which means equities come from combining hundreds of other cubeful equities. In general, you have to iterate over all rolls, pick the best move for black for each roll, sum the cubeful equities of those best moves, and divide by 36. The equities for this Frigo-Mochi position, for example, depend on about 1 million positions, 35% of all possible positions with 7 checkers or less. But this is exactly what computers were born to do. Obviously, we are careful to compute every position just once by going backwards and storing the results for quick access later. This explains why we can do it only for a small subset of pure race positions. Computing up to 13 checkers per side on 6 points, which I did, requires storing 8.3 gigabytes. But even to do that, we had to get lucky. To compute the initial double take, we need the cubeful equities with white holding a 2 cube. For those, we need equities for black when white holds the 2 cube and when black holds a 4 cube after a redouble. And for those, we need the 8 cube equities, and so on and so on. It seems we need an infinite cascade of equities for each position. But fortunately, this is not the case. Say white redouble to 4, and we need the double take equity. After a take, it's white to move, with black holding a 4 cube. But look, by some miracle, the board on the next table has the exact same position. Only there, black is holding a 2 cube, and they are playing for 2 lira per point. So the two tables are identical. Same position, with white to play, black holds the cube, and each point is worth 4 lira. So the equity of double to 4 take is exactly twice the equity of double to 2 take. The cube value is not important. It's cube ownership that matters. Centered, owned by black, and owned by white. So we need just 3 values which correspond to the 3 types of ownership. Centered no double, double to 2 take, and no redouble holding a 2 cube. We just need to be careful to use the right kind of equity when combining equities and determining best moves. This concludes Doubling 101. Stuff you probably know, but basics never hurt. That said, you didn't click for basics. You clicked to learn something interesting and useful, which you will if you stick to the end. So let's get going. Gigs of data let machines play perfectly, but we humans need concise rules and visual aids. So let's use the data to explore the relation between cubeless and cubeful. Here's a plot of position type, no double, double take and double drop, against its cubeless win probability. This is the so-called doubling window, the win probability range of double take positions. And as you can see, it's very well defined, almost no overlap between the 3 types. This suggests that anyone good at estimating cubeless probabilities will be a very strong cubeful player. Aliens and bots come to mind. We just need 2 thresholds, 3 actually, because the redouble window is slightly different. The drop point is the same, but the redouble point is higher than the double point. Question is, how do we determine those thresholds? And how do we evaluate the effectiveness of this or other methods? Not easy questions actually. In fact, there's no best thresholds because they depend on the probability distribution. Some positions come up more often than others, and anyway it depends on who's playing. However, they probably lie in a very small range. So I simply collected 1 million pair of positions using bot self-play. This sample spans the whole range, positions going from a few checkers up to 15. I can't do all pair of positions, but I can do individual ones. It essentially requires a deep evaluation, which goes down ply after ply until reaching a position with 13 checkers or less on both sides. It might require one evaluation or many thousands, about 1500 on average, so certainly feasible. It's a practical compromise, and I'm pretty sure no one ever computed 1 million exact cubeful equities. We shall use it to find the best thresholds, and also to compute the doubling, take, and redoubling error. The doubling error is the method mean equity loss over the whole set, and same for the take and the redouble. Here are the numbers for our cubeless money player when using the empirical thresholds. This is probably the best that can be done without involving deeper plies, which leads to the question: what can serve as a lower bound? Pip count is a standard basic measure, so it's natural to relate it to cube actions. Here's a plot of PCDs against win probability. Not a pretty sight, but we can fit a line through the mess and find the PCD values corresponding to our double and take points. The result is awful, so let's ignore it and figure out the thresholds directly from the data, just like we did for cubeless. This gives take 44, our basic money doubling method. Double if leading by at least 4 pips, and take when trailing by no more than 4 pips. So it's a double take at exactly 4 pips difference, no double or double drop otherwise, and redouble when leading by 6 pips or more. Here are the error measures for take 44. Much worse as expected, but what do they actually mean? Separate error measures don't tell us anything about the actual skill difference. So we turn to the ultimate test, playing against Hal, the perfect cubeful player. This measure uses another set containing 1 million first entry positions, the first bear-off position encountered in a game. We try to minimize luck by playing each position twice, with color reversed, and both times the dice and moves are exactly the same. So each method faces the exact same decisions. The total points won by each is converted to win percentage and then to ELO. Turns out, cubeless is 5 ELO points short of perfect, and take 44 is 192 ELO points behind. And what lies between? I picked 6 methods, 5 from Tom Keith's excellent online article, and 1 recent contender, circa 2014. The first is known as 8-9-12. Black doubles if she's 8% ahead in the race, redoubles if she's 9% ahead, and white takes if he's no worse than 12% behind. Second in line is Kleinman. The Kleinman count transforms the pip counts to big K, and K determines the cube action using the threshold shown. I put it in because commentators sometimes mention it with reverence. But look at the numbers. Not only it's the least practical, it's just terrible. It's so bad, I thought I made some mistake, and so created the figure of K versus cubeless win probability. It's messy like any method using just pip counts, but you can see the shadow outlining the density, and the K values corresponding to the cubeless thresholds seem to match the values in the literature. So I think I got it right. We'll get back to this and other anomalies soon. The other 4 follow a more traditional route. Compute the pip count, correct for wastage, correct for number of checkers remaining, and gaps, and finally apply some thresholds. Thorpe adds 2 pips for each checker on the board, subtracts 1 pip for each non-empty point, and adds 1 pip for each checker on the 1 point. Finally, if black's adjusted count is greater than 30, it's bumped by 10%. Thorpe doubles when at most 2 behind, redoubles at most 1 behind, and white takes when no more than 2 behind. Ward also adds 2 pips for each checker on the board, adds 1 pip for any gap, and then 2 pips for each checker above 2 on the 1 point, and 1 pip for each checker above 2 on the 2 point. 10% added throughout. Ward uses the same doubling window as Thorpe. Keith doesn't penalize for extra checkers. He adds 1 pip for any gap on the 4, 5, and 6 points, and then adds 2 pips for each checker above 1 on the 1 point, 1 pip for each checker above 1 on the 2 point, and 1 for each checker above 3 on the 3 point, and black's count is bumped by 14%. Keith doubles when no more than 4 behind, redoubles when no more than 3 behind, and takes when no more than 2 behind. Eyesight, like Keith, has penalties for extra checkers and gaps on the 4, 5, and 6 points, but a gap counts only if the opponent does not have a gap on the opposite point. It adds 1/6 of black count, not 1/7, and doubles when 6 behind or better, but takes when at least 2 ahead. Those are the 6, and this is the updated performance table. Predictably, there are 2 camps, the pips camp and the pips plus benefits camp. Pips alone are too weak to push the cart, and it's time we relegate them from the self-help section to the history or fantasy section. Still, it's educational to understand where those large skill differences come from. Let me illustrate using one first entry position. With optimal play, white doubles on the second move, black takes, and play proceeds until white wins 2 points. But see what happens when Kleinman plays cubeless. Kleinman takes, and then redoubles and take, again and again and again, until the cube reaches 128. In contrast, when playing take 44, 44 not only misses the double, but drops the cube to boot. It's our old friend, style. Kleinman is bold and wild, and can take advantage of timid and conservative 44, but pays dearly when faced with stronger opponents. Bear-off games produce extreme ELO discrepancies. One-on-one, Kleinman is 59 ELO points stronger than take 44, but he is about 750 ELO points weaker according to Hull. So let's put pips only aside and focus on Thorpe and Sons. All 4 are feasible over the board, but do require some work. So I wondered if there's anything simpler. I tried this and that other thing, and it became clear the second most important statistic after pip count is the number of remaining checkers. So meet pipping. Simply add 4 times the number of checkers to the pip count and take the difference. It's not surprising to see this 4. 8 pips is about the average roll, and if you bear off 2 checkers per roll, then 4 pips per checker is another optimistic pip count. Pipping doubles when at most 1 pip behind, redoubles when leading by at least 1 pip, and takes when at most 1 behind. Pipping ignores gaps and wastages, and yet does very well. Too well actually. And worse, 3 minor adjustments bring it to the top of the board. First, bump X pip count by 10%. This counterintuitive measure of increasing the pip count for the side about to roll seems to do wonder. I'm guessing it compensates for the power of the cube given to white. The second important adjustment is to separate short and long races. For short races, ignore odd number of checkers by rounding them to even. So 1 and 2 checkers count as 2, 3 and 4 count as 4, and so on. And most importantly, use 2 different doubling windows. Double when 2 pips behind or better and take when at most 3 behind in long races, but double aggressively and take conservatively in short races. That is, double when 4 pips behind or better and take only from 2 pips up or better. This brings pep count to minus 45 ELO against Hull and straight to the top of the board. This unexpected success should have raised multiple alarm bells, but I was too happy with my baby, and it took me a while to figure out what's going on, and also to get a better grip on the style issue, because style was still causing havoc. For example, how come Eyesight beats Thorpe, Ward, and Keith, and yet weakest against Hull, and substantially weaker than pep count? What's going on? And how did I mess up this time? The breakthrough, if you can laughably call it that, arrived when I did the obvious and split the error measures. Doubling error, for example, is made from missing a double and from doubling too early, and I lumped the two together. Same for takes. You either take when you should drop, or drop when you should take. Look at the refined error measures, color-coded. Eyesight doubles and redoubles are marked red, because eyesight doubles aggressively and rarely misses a double. I named them for convenience. Doubling can be brazen, timid, or meek. Brazen means very aggressive, doubling too early. And timid is the opposite, when the bulk of errors comes from missing doubles. Meek is similar to timid, but less severe, say within a factor of 2 between the two types of errors. For takes, we have a bold and daring. Both are optimistic, favoring takes over drops, but bold is more lopsided, and daring less so, again within a factor of 2. Now, it's easy to see what's going on with eyesight. Eyesight doubles early, redoubles aggressively, and takes boldly. The cube gets high with eyesight, early and often, and Thorpe, Keith, and Ward fail to punish her due to timidness. But pep count, taking responsibly and redoubling more aggressively, can temper the boldness. It's nice to have an explanation, but it raises the question: how come those well-researched methods exhibit such imbalances? It's actually easy to find the reason, now that we have a proper view of the data. The doubling windows are off. But don't ask me how or why. Perhaps I misunderstood the English, which happens occasionally, or the data used to develop the methods was fundamentally different than mine, or maybe the doubling windows were optimized for longer races, and I'm doing only Beroff. I'm truly baffled, but I do stand behind the way I created the validation dataset. Play from the start position until breaking contact, then play on with LiveCube to Beroff. The resulting set should be an excellent sample of the positions likely to come up in your games. So here we are. I'm not sure which doubling windows were used by the creators of the methods or being used today by players over the board. But I do know what the data wants, which is these doubling windows, smaller and mostly deeper windows. And they make quite a difference. Keith rises to the top, but the difference between methods shrunk by a lot. All are amazingly good, getting very close to perfect given the relatively crude counting. And style is still with us. Keith does well by doubling and taking boldly, then limits damage by redoubling timidly. Pep count meekness works well against everyone but Keith, and eyesight does better against everyone but pep count, and yet is the worst against Hull. So what can we make of it all? First and foremost, cube actions are hard, and nothing trumps experience and good judgment. But it's great to have an internal phone a friend, and any adjusted pip count method will do, provided you use the right cutoffs. These methods are not perfect, but very effective guides. I just missed a double because I was too timid to follow my own advice. Only note that while pep count correctly classified it as a money double take, it is a big drop at the score. I'm sure Justin would have had some witty yet harsh words to say on my miss. Only Justin will never comment on my games. Lucky escape for both of us, no doubt. But you might get to be on stream one day, provided you keep learning and start paying attention, like I did, to the interplay between pip count and the number of checkers. Great, you say, but Pepe, which one should I use? Which one is the best? Surprisingly, I have an answer. It's not 42. But you're not going to like it. You're really not going to like it. So first, let me give you my thoughts. Life is a game of choices, a game of give and take. So, if you have no favorite, Keith looks like the safest bet. Or maybe consider pep count, which is almost as good and might be easier to apply over the board. And on the third hand, it might be best to pick the method you find easier to compute, because some method is better than no method at all. Just remember that none of them are best, because the effectiveness of any imperfect doubling strategy depends on the opponent. These are my thoughts. Now to the best. Practice all three: Keith, eyesight, and pep count, and use M3, the majority vote among those three. This will land you 32 ELO points short of perfect and nicely up against all others. Is it better? Yes. Can you do it reliably over the board? Maybe. Is it worth investing all this energy and time on and off the table? No idea. Thank you for reaching the end, and if you learned something interesting and useful, you know what to do. Happy cubing, everyone. Adio.